So here we go, brainstorming about probability. When I get going with this, it's starting with we're going to go through all sorts of things here. So when I first think of probability, I think of more like what the definition of probability is. And that is likelihood of something happening. So it's likelihood, another word that we use. All right, and it's number of what we want divided by all possibles. All right, so the number of what we want, so the probability of some event X is equal to the number of what it is that we're looking for, how many ways does that happen, and what we're looking for, divided by all possible outcomes. And when we're doing this, we recall that probability as well, when we're in this case, probability of some event X has to be no more than 1 and is going to be at least 0. Probability can never be more than 1, can never be less than 0. And when we do probability, we're also going to talk about, these aren't going to connect. All right, might have to change my thoughts on this. Anyways, all right, then probability, the other thing that I think of when I think of probability oftentimes is this big idea of independence. Independence. And independence is knowing one event does not influence the likelihood of another event from happening. So I would be writing this down. It's kind of like being a flashcard here. So this would be knowing that one event happens does not influence the likelihood of another event happening, and that's independence. And we can prove independence a couple different ways. We can do if probability of A and B equals the probability of A times the probability of B. If that is true, then that means that these two events, A and B, are independent of one another. All right. Another way to say that is if the probability of A given B is equal to the probability of A all by itself. So if I know B, and then I find the probability of A, and if that's the same as just A all by itself, then that means that knowing B did not change the probability, therefore they're independent. All right. If I know they're independent, then I'm definitely going to be using this formula. All right, for independence of probabilities. And independence is a big idea. You should expect that at least on multiple choice, and if not on a free response somewhere, you're going to have to address the idea of independence and how that's going to then impact finding and calculating probabilities. All right. So some of this stuff here is I'm just going to have to get out of the way and shrink up and move in order to make space for everything else. We'll put this there. All right. Independence, I'm also going to throw over here, I'm going to do a Venn diagram. Here's my Venn diagram. And I'm going to have A. I'm going to have B. Pretend it's entirely inside. I'm going to have C. And I'm going to have D. D is my rectangle. All right. When I have something like this, this little shaded area here, that little shaded area is B intersect C. Okay. And B intersect C might be independent. In a Venn diagram, you cannot prove independence. Once again, in a Venn diagram, you cannot prove that two events are independent. All right? We can, however, prove that two events are definitely not independent. So what do I mean by that? So we have C is disjoint from D. All right, what does that mean? That means if we look at C, I'm going to color C in with red here. So there's C. Is that oval for C? And then I've got D over here, which is my rectangle. All right, disjoint fancy name for they do not intersect. They have nothing in common. You could also say they are, there's another word, actually two words, mutually exclusive. Mutually exclusive events is the exact same thing as disjoint. It means they don't intersect. All right, so then I'm going to go like this. Probability of D given C is equal to 0. So what do I mean? Let's take a look at that. If given C, so this is given C, if I am in C, so I'm only in red, this is my given, so instead of being out of the whole thing, I'm now only out of the red. If I'm only in the red, what's the likelihood that what's the likelihood that I'm in blue? Well, if I'm given that I'm in red, there is no chance I can be inside of D, which is why the probability is 0. Probability of D itself, it looks like there's stuff in it, so it has to be something at least 0. All right, so probability of D is greater than 0. So D all by itself is something. The probability of D happening is some value because D is right there. There's something in D. All right, but if I know that I'm in C, I can no longer be in D, so now the probability of D is 0. The D cannot be equal to 0 and greater than 0 at the same time, which is why D and C are definitely not independent. Knowing C changed the probability of being in D. This I can prove from a Venn diagram. Mutually exclusive events are definitely not independent. This will show up on like a multiple choice sometimes, and my recommendation is if that does, is draw a Venn diagram and see if you can make sense of what they're actually asking. All right, so let's shrink this up. And I don't know why that's all by itself. We'll make that smaller, put that over there. Now, what should we talk about with probability? We got the different probability rules. All right, so I'm going to go blue, rules over here. Probability of A and B is equal to the probability of A times the probability of B given A. And that's if I do not know anything about A and B being independent. If they are independent, then I can get rid of this. Just cover that up. And I would have, if A and B are independent, then the probability of A and B is equal to the probability of A times the probability of B. I've also got this, A or B. In a Venn diagram, that means I'm in A, B, or both. All right, so back in this picture over here, it's everything inside of A, the whole circle, and everything that's inside of all of B. So it's all of B, all of A, and it's that middle portion. But remember, if we're doing it like that, if we first do A, and then we do B, I've counted this little middle intersection twice. So this will be equal to the probability of A plus the probability of B minus the probability of A and B. Because you can't count that area twice. Those are the two rules for probability. Just recall or, and. Intersection, union. All right, so what else do we know about probabilities? Oh, then we started doing stuff like, what if it's one type of probability that we were doing as a binomial? That's going to show up again, binomial. In binomial, there are 4 conditions. First condition is independence. That is, knowing one event happening is not going to change the likelihood of another event happening. So every roll of the dice is independent of all previous rolls of the dice. If I draw a card from a deck and look at it, mark it down, put it back into the deck, shuffle it up again really, really well, the next draw will also be independent. If I draw a card out of a deck, I don't replace it, now it's no longer independent. All right? Binomial, there are exactly two outcomes: success and failure. 3, the probability of success is constant. Trust me, that word is constant. So P is always going to be the same thing. So if you're talking about drawing a queen from a deck of cards, and you put the cards back and shuffle each time, queen would be 4 out of 52. It stays the same all the time. And then the fourth is there are a finite or a set number of trials. All right, set number of trials. And then we got the binomial formula. Remember this? I'll try to draw this neatly. Probability that x equals k, if it's a binomial, is equal to n c k. That's combination here. N is, remember, n is the total number of trials. So total number of rolls of the dice, total number of children that you have, total number of people in a line, whatever it is that we're talking about. K is the exact number of successes. And then that's going to be times P to the K, where P is the probability of success, and it's raised to the K power because that's how many successes I want. So I want this to happen that many times. So I take it to that power. And then Q times Q, I'm going to write it as 1 minus P, same thing, to the N minus K. All right. So again, this is the probability of success, and it happens K times. This is the probability of failure. Remember, P and Q, remember this whole thing here, 1 minus P is Q. They're complementary events. They add up to 1. All right. And then this is the total number of failures. Number of successes, number of failures should add up to total number N. And then I added a new slide. So in terms of binomial, the extension from that is what we call the geometric. The geometric probability distribution is, it's still independence. There's still, P is constant. We have exactly two outcomes, but we do this until we get the first success. So we proceed until first success. Okay, an example would be if you're a hunter and you're not a good shot. Let's say that the likelihood of you hitting an animal with your weapon is 0.47. So again, you're not a good shot. 47% of the time you're gonna hit the target. All right, you're gonna keep shooting until you hit the animal. And you're just gonna hit it once. So we're gonna call this the likelihood of a lethal hit. All right, so we'd say in that case, let's assume that every shot is independent of all others. What is the probability that you get the animal on the first shot? Well, it would be 0.47 because there's a 47% chance. What is the probability that you hit the animal on the second shot? Well, that would be equal to 0.53 because you missed it, and then times 0.47 because that's the second shot. What's the probability that you hit it on the fifth shot? Fifth shot would be, well, 0.53 is miss. And how many misses did I have? I had 4 consecutive misses, then the 0.47 for a success. All right, and these are all geometric. All right, this would be the likelihood of it happening on the first trial, second trial, on the fifth trial, and so on and so on. And that's a geometric distribution. All right, for probability, what else do we have going on for probability? When putting problems together, another thing I like to do is just do tree diagrams, because sometimes this can help with deciding, what you're going to do next. All right, so we set up these different probabilities. So let's say this would be male, female. So let's just say it's 50-50. And then there's 3 options within that. So let's say this is, I don't know, A, B, and C. And male, female, and A, B, and C. So this line right here, and let's say this is 0.2, 0.3, and 0.5, would be the probability of male and A. All right, and so that would be equal to probability of male times the probability of A given male. All right, and this is 0.3, 0.2, and 0.5, we'll say. And you could carry out this whole tree diagram. These values here for this step have to add to 1. And then the second thing that happens, those have to add to 1. These have to add to 1 because those are all the possible outcomes. So you did this one thing, and then you're going to do one of these 3 things. All right, since there's exactly 3 possibilities, those 3 things have to account for everything that's going to happen. Those probabilities have to add to 1. Then, when you're doing this, if you've done it right, you're going to have 1, 2, 3, 4, 5, 6 different probabilities. All of those probabilities will also add up to 1. All right. And then let's say we're doing another Venn diagram, and we're going to have A, B, and C, and they start plugging in values for what numbers are here and what numbers are there. Again, all the probabilities in a case like this also have to add up to 1, because then that would be what we call probability distribution. Probability distribution. And usually when I've said, let's see if I can spell, and see if you can actually read what it says. Probability distribution. We're going to have X, which is number of successes, and we're going to have probability of X. 0, 1, 2, 3, 4, let's say. And then the probabilities that go with it. These probabilities, those are not zeros, I'm circling them. Each of these, if you add them all up, also has to equal 1. And that's what a probability distribution is. And then we go, oh, right, probability distribution. And then I can also find the mean of a probability distribution, which is also called the expected value of X, which is equal to the probability, let's change that. The sum of every probability of X times that X value itself. Usually these are written in the other order, so this would be in front. But you would take 0 successes times the probability that 0 happened, plus 1, which is from that distribution table up here, right? I got 0 and I have 1. All right, and times the probability that X equals 1, plus and that gives you the mean of a probability distribution. And I know there's more, but this is just a good start to get you thinking about probability, more thoughts on it. I did not cover everything, but I want you to keep going, keep thinking through things, and then when you've exhausted everything that you can think of, then go back to your book, look at the chapters on probabilities, look at some of the words and the language, and add it to your giant web that you're creating of all of these ideas as you brainstorm about the probability aspects for the AP exam. That's a lot of talking. I just talked really fast, and now I'm ready to take a nap. So get on it and keep going.